Hello, this is Lenny. In this video, I would like to teach you how to use the space colonization algorithm to build a tree-like structure. Okay, let me first introduce the algorithm. In this algorithm, at first, we will scatter some points. Okay, these points are called attractors. You can think of it as the food, or we call it attractors. The food for the tree to grow. So these the points will define the overall shape of the tree. Like I want the tree to be grow like this. So basically I will scatter my points like this. These are my food, my attractors. And then we have another type of point. It's called the node. The node is where the tree is actually growing. Okay. So at first we will assign some attractors as node. Okay, this is node. I want the tree to be grow from here. Okay. And once we define these two type of points, we needed to define another three key values. That's called the move distance and the remove distance on the search radius. So at the first step of the algorithm, the first step is for each node, the first step is for each node. We use the search radius. We search our nearby attractors. Okay, we search our nearby attractors. So at the first frame, we only have this node. We use assume we have a search radius like this. So we search our nearby attractors, and this point are all our attractors. So we collect it, and then we calculate the average direction of all these attractors away from us within the search distance. So this is the average direction. We have a scalar and a direction. And the next step is we use the move distance to move along these directions. So let me draw it clearly. I use the move distance, assuming the move distance is, this is the move distance. So we use the move distance to create along this direction, and create a new node. Okay, and then we use the remove distance to remove all the attractors within, like this, and these attractors will get killed. Okay. Let me draw it again for clearer view. At first step, these are the attractors. Okay, the black one is called the attractors. The food. The attractors. And the red is called the node. This is where the tree will actually grow. So assuming this is the first, at first step we only have one node. We can have multiple nodes. That's fine too. And we use the algorithm start. We just use the search distance, and for each attractor, it will attract it to the node. Okay, if it is within the radius, the search radius. This is called the search radius. So we should loop through every attractor and use the search radius. Like for this node, it will attract it to it. And for this knot, it will attract it to this knot, okay? And for this, these are too far away, so they won't move, okay? And then we just, for this knot, we move in the average direction of the attractors we have collected. So the average direction is like this. And how long should we move? We have defined the move distance. So assume we have move distance like we say this. We move a huge step. That's fine. And we just have to create a new knot here. And then once you have moved, you have to use the remove distance to remove your nearby attractors. So we will remove this, and this. Okay. Then you repeat the algorithm. So now we have two knots. And then we just run the algorithm again. And for each, just again, yeah. So let's start to implement this in Houdini. So at first I wanted some points to be acted like attractors. So I will use a sphere, prime polygon. Let's increase the frequency. And I want it to be a little bit distorted. And let's move it above the ground, like this. Okay. And I want the trunk, so let's make a tube. It's too thick, like this. Yeah. And I want it to be end caps and polygon. Yeah, it looks good. So we just merge it. Now we have the basic shape of the tree. So what we have to do now is we wanted to scatter some points also inside the volume. So I want to use the VDB from polygon, and we create a fog, the density field. Okay, and I also check the field interior. So the more inner of the volume, the denser of the fog. So I will scatter more points in the interior. Let's reduce the voxel size. And let's scatter some points. Maybe, let me uncheck field interior. Nope. I want more points below, so I will increase the radius of the, yeah, like this. Oops. I don't want to relax the points because it's more natural. And okay, I like this. So these points will first be act as our food, our attractors. So I will just create a group and code all the points as attractor. Okay. But I wanted to also assign the initial point, like this point, the 412. So I wanted to create another group that's called the node. Okay, and it's the point attribute, and I wanted to assign 412. This is our initial node. Okay, and then I wanted to use group combine because I don't want the node group to also contain the attractor group. They are overlapping, so I wanted to Actually, what I wanted to do is to subtract the attractor from the node. Okay. Oops. Oh, some typo. ATTRA attractor. Yeah, I wanted to subtract the node group. This is the node. These are the attractors food. So this point, the 412 will act as our initial growing point. And the next step is I wanted to define the move distance and the remove distance and the search radius. Okay, so let's create a point triangle. And for each point, I wanted to store the move distance and the remove distance because I want to have some for different points. I want different move distance and remove distance. Okay, so I will store them not in the detail but in the point. I call it move distance, and let's just call it move disk, and then remove distance. Just call it remove dist. And let's create a variable. The initial value, I think I will set it like this, because yeah, we will modify it later. Experiment with that. So for each point, we just define move distance and the remove distance. Okay. Okay. Let me create a network box and comment. This is create overall shape. Create points. Create all the points for overall shape. And then, yeah, I think we could start the algorithm. So we just use a solver and jump inside, and we will just run the algorithm I'm just saying. So first I will use a wrangle node, attribute wrangle. Before that, I will want to for each node it will store who is my nearby attractors. So I will need an array to store my nearby points. So let's call it near points array. This will store the point number. Store the point number to nearby attractors. Okay, that's good. And let's create another wrangle node. So this is called init nearby array. And then now we want it to run through every food attractors. It will attract it to the node. So we just first we have to get our search radius, but I haven't defined it, so I will define it here. The search distance, and then we just wanted to find our if there is any nearby node within the search radius. So close node, I use near point to find is there any node in the node group that's and our position, and then the search radius that's within our search radius, search distance, sorry. And then I will just append it to the array I just created here. So this is called append and array. Now I wanted to set point attribute to set our mean near point, the near points. Okay. the near points array, and this is the closest node we have found. So est, the closest node, and I wanted to append, so it's called append. Okay, so far so good. Yeah. So for each node we created a nearby array which will store who's our nearby attractors. So now we just run through every attractor and set the array. Hey, and told the node, hey, I'm your food. You can eat me now. Okay. So this is called set near points. Now I wanted to the next step is we calculate the move distance and the remove distance for each node. That's how far we should move. So now we have, for each node, now we have an array that's telling me who's my neighbors. But the near point is empty. Why? I think because the move. Oh yeah, I just forgot to set the search radius. So I will search like 3 like this. So let me reset simulation. So I think yeah. You see, our initial node has near points. These near points store our nearby points, which is affected by search distance. I want to make it smaller. Yeah, like this. And what I wanted to do now is to use these near points to calculate the average direction we should go. Okay. So for each node, we get our near points that store in near points, and I wanted to know how many near points I have, so get the length. Okay, and if I don't have any nearby attractors, if I don't have any food, I just wanted to return. We don't have to run the algorithm, just skip it. So I wanted to initialize some variable first, the move direction, the average direction I should go, and the move distance is no, I will initialize this later. So I just loop through all of our nearby attractors, near points, and calculate the direction I should go. I'll just go point, and I want the position, and I have the point number, and minus our current position. And this will calculate the calculate the average direction we should go. Okay. And then I wanted to normalize it, because for each node we have already stored the move distance. We know the distance we should move, the step we should move forward. Okay, so this is our move direction. Now we just wanted to create a new node. So I wanted to create a new node by stepping forward. So this is a new node number. I'll call it add point 0p current position plus the move direction, and this is a scalar and the direction. And I also wanted to set some attribute, a set point group, because it's a node. Okay, and set it as 1 because I just created a new node. We have just stepped it forward. Okay. Let me say it more clearly. I have just this is the node. Whoops. This is the node, and these are the my nearby attractors. And now I have just calculated the average direction I should go and the move distance I should move. So I will create a new node. So I create a new node. Okay. And it's called the node group. So far so good. But I also wanted to, because I store every move distance and remove distance in the points. So I also wanted to set the move distance and remove distance. And I just wanted to use the average of the food I have eaten, the average of the attractor's move distance and remove distance as the new value. So we also calculate the we also have to calculate the average move distance, okay, and the remove distance. And let's just calculate the average. Move dist plus 0.0. I wanted to get the move dist and near PT, and then remove dist. I wanted to get the remove distance near point, okay? And then we wanted to calculate the average. So what we have to do is just we divide it. So move dist is divided by float, the number of near points. Yeah. The number of near points. Yeah. And for the remove distance, we do the same thing. Float divided by near points. Okay. So now we have the we can set our new attribute. So we just call set point attribute. Okay. And I wanted to set the move dist and the move dist, yeah, and also the remove distance. I'll just copy it, paste it, remove distance. So far so good. Because I have added another new node from here to here. I want to create a polyline between them, okay? Just for visualization. So int new primitive is equal to add primitive. I wanted to create a polyline. And from the point number to our new node. Okay. So far so good. Okay, now the last step. So this is called the let's call it expand node. Okay, and then once we have expanded, you see now we've got a point. We calculate the average distance. Then we have moved forward. Now I wanted to use the remove distance to remove our nearby food. That's extremely easy. Just call another attribute wrangle node. Again, we run through every node. Okay, it's a point, and we just find all of our nearby attractors. So near attractors is equal to near points, and then we wanted to find the attractor, our nearby attractor. Okay, and that's within the remove distance. Okay, that is to say we have moved forward. So I wanted to use my remove distance to remove my nearby food. So now we just have to run through our nearby attractor. npt near attractors, We just want to remove it, so we call remove point 0 PD. And is there a problem here? Oh yeah. So you see, we remove lots of points are nearby. Okay. Remove distance. I think remove distance is too strong. But that's fine. We can see. Yeah, you see the algorithm is starting. We move forward and remove. We calculate the average distance we should move forward and then just remove it. Okay, that's fine. Yeah, that's basically the space colonization algorithm. So the last step is just we wanted to remove the some attractors that's left. So I wanted to delete the points, attractors, food that are not eaten. So we can just use a poly wire to create a thickness. Okay. If you wanted to have some variation of the the older the tree you want to grow thicker, the yeah, you can just we can just store an age attribute. For each loop, we just increase the age. Okay, I will leave that as homework for you. But now I wanted to talk about here when we are init parameters, the move, remove distance, and remove distance, and we just set it for uniformly for each point. Maybe we can add some variation. The higher the tree, I want the move distance and the remove distance to be smaller. Okay, so what can we do? I will use the height to remap the move distance and the remove distance. So let me just use an attribute promote. And I wanted to find the position and promote it to detail. I want the minimum. Where's the minimum? The minimum, I call it main P. So now we have the minimum position, and I wanted to trade promote it again to get the maximum of the position. So P maximum max P. So this is called get min P. This is called get max P. Now I just wanted to use a point varp to remap the move distance and remove distance based on the height of the tree. Okay. So call it remap parameter move test. Remove and remove test. We jump inside. First we will get bind our variable. Yeah, it's a vector and it's called max P. I wanted to also import the min P. It's also a vector. And I'm only interested in the y value, so use vector to a float to get the y value. Okay. Now I just wanted to use the fit and plugging the source min, source max. I wanted to remap it to 0 from 0 to 1. And we also needed to get the y of the p. No, we just get the, let's put it in CD. You see, we get from 1 to 0. Okay, I want to use this value to remap the move distance and the remove distance. So let's just import them. Move dist and then remove dist. And then I wanted to what should we do? We should use a ramp here. No, first I will I will ramp it. Use a spline ramp to ramp the value. This is map move remove map remove distance. Okay. You may want it to just leave it here and multiply it with the move distance, and then we just bind export. So move dist. So far so good. Now I wanted to ramp another ramp for the remove distance. So where's my, I don't want color ramp parameter. Why I can't choose the type of the ramp? That's weird. Not sure why. I don't want the color ramp. Oh, I think the problem is the name collision. So I will call remove ramp. Yeah. Sometimes you have to be careful because the name will collide. Okay, I'll just recreate it. Ramp. Call it move distance. And what? Oh, another name collision. So this is called ramp move distance. This is called ramp move distance. Sorry. So I will use this to multiply the result and bind export the remove distance. Okay, now we have two ramp, and just wanted to tweak it. Like this, and just plug it into our solver. Now you can see, yeah, I think I have, yeah, I should put it like this. And this. Yeah, now you see the higher the tree, the move distance is smaller, and the lower the tree, we move at a larger step. You can see our point here. Oh, let's sort it by y. You see the higher the y, the move distance is extremely small. And the lower the y, the move distance is move at a larger step. So we can use a ramp to control the move distance and the remove distance. We can even include the search radius, but it will bring more complex, a little bit cumbersome, but it's fairly easy to do. Yeah, so you can see, yeah, our tree is basically finished. I would like to use a smooth here to smooth the tree. You see, we now have a special tree like this.